Among all routing protocols, Ospf is very popular. The reason is this is the protocol which can scale to any size network. A small network, a large network, any size network, doesn't matter. Any size network. This will fit in. See, all of the protocols have some limitation. This don't have hop count limit. There is no hop count limit. And the metric is based on bandwidth. So compared to various other protocols, this has got a lot of wonderful features like areas. Whereas if you take EIGRP, you form one autonomous system. You cannot have too many routers in an autonomous system. More you have, more problem, more difficult to maintain. That's not the way Ospf is. Ospf has got a very good hierarchy design. A very good hierarchical design. Ospf. So open shortest path first is a link state routing protocol. That's another advantage of this protocol. It advertises the link status rather than routing table. Advertising link status rather than routing table. So Ospf collecting all the link state information can build a wonderful database with complete topology information, using which SPF algorithm can pick accurate, best, low-cost path. More accurate path selection based on the cost can be achieved through that big link state database, which Ospf maintains by collecting link status advertisements. Now the O stands for open. It's an open standard protocol. O, open. SPF, shortest path first. It's an open standard routing protocol that uses shortest path first algorithm, which is also an open standard algorithm. Though the designer of this algorithm is a man called Dijkstra, he has given this as an open standard algorithm. So if you heard about Dijkstra's algorithm or binary tree algorithm, SPF algorithm, all three are same. These all three are same. All right, so open shortest path first is a routing protocol, but SPF is just an algorithm which is used in this routing protocol. Yeah, so let's learn about this protocol. As I said, the routers will advertise link state information to one another But when will this advertisement be done? Only for after finding neighbor. I repeat, this is not the very first thing in OSPF. It's not, just send advertisement just like that. First of all, it will identify the neighbor, then it will send this advertisement. So you should not get misguided with this information. So we need to understand this. Don't think, very first thing between the routers are LSA advertisements. Not really. First of all, the hello packets will go between these routers, and the hello packets are sent to multicast address 224.0.0.5. Because they do not know who the neighbor is, it cannot share anything. First, it needs to identify the neighbor. For that, the hello packets are sent by every router periodically every 5 seconds. Is it true or false? Is it every 5 seconds or 10 seconds? Very good. In OSPF, it is only 10 seconds. So every 10 seconds, these hello packets are going to discover neighbor. Hello packets will be useful. Once the neighbor is discovered, they undergo various states. Only during the exchange state, this thing happens. We have something called init state, two-way state, extart state, and then exchange state, and then loading state, and then fully synchronized full state. So what I'm trying to say is, to build this LSDB, the synchronized LSDB takes time. It is not immediately very first time it happens. First of all the routers should know each other, and then they will send whatever they have, and then those things are collected by each router inside a memory location called link state database. This link state database now got the complete picture of the topology. Now, this topology that is built on each router will use this algorithm called SPF in order to find for each destination, let's say this is the source, to go to this destination, this is the shortest path. It won't try to take any other direction. Likewise, to go to this point, it will take this direction. So every router has got this database, and every router will position themselves in the database and try to find the best path. And that best path is installed into this routing table. So only the final elected route comes into the routing table. If there are multiple paths, say for example, A has got 2 paths to reach this network behind C, 1.1.1.1. Let's say the cost is here 1 and 1 and 1 and 1. So if you go this way also, it is 1 plus 1 plus 1, 3. If you go this way also, it is 1 plus 1 plus 1, 3. OSPF can take both the paths. Yes, equal cost multipathing is by default supported and enabled in OSPF. It is by default enabled. Equal cost multipathing is by default enabled. Okay, if you have many paths, how many paths will be there in the routing table? You see, equal cost multipathing is supported through if you have two paths like what you have in this picture, two paths will be there in the routing table. What if I have 20 paths equal? 20 paths to destination with equal metric. Will all 20 be seen in the routing table? No. By default, only 4. But you can tune the Ospf to have up to 32 paths. Okay, up to 32 paths. We can tune you can tune it. You can simply go to Ospf, router Ospf, and say max path. You can say max path 32. All right. So do you have any question? Nice. You know, there are three tables like EIGRP and BGP. OSPF also got three tables like EIGRP and BGP and ISIS. This also has got three tables. Number one, neighbor table. As I said earlier, the table which has got those routers that formed successful neighborship. See, I told you the hello packets are sent, but these hello packets, if they don't match certain criteria, then it cannot form neighbor. It needs to form certain criteria. Yes. So hello packets, when they meet the criteria, that makes it to be eligible to form neighbor. Those neighbors, established neighbors, will be seen in the neighbor table. About the topology table, I already told you. After forming neighbor, all the routers share their database, link state advertisement. All link state advertisements together, we call it as LSDB, but summarized version of it is called as DBD. DBD, database description. Yeah. So those DBDs are collected and each router forms LSDB. And this LSDB is what we spoke here. All right. So that is another table. We call it as topology table. Now this LSDB will be unique. This LSDB will be unique among all the routers that are in same area. Yeah. Within the same area, all will have unique database. What does that mean? Between one area and another area, it may not be unique, but within the same area, it's going to be unique. Next comes the routing table. Routing table, as I said, it will have only the best path. Using that path only, packets are forwarded. Router will never use topology table paths. Topology may have 1,000 paths, but only the elected path which is kept in the routing table will be used in the routing table. Now, why is link state routing protocol so important? See, compared to any other routing protocol, link state protocol can provide more information because link state advertisement is what? Shared. Because it is link state advertisement that is shared between the routers. It's not the routing table shared. See, when a routing table is shared from one router to another, only the best path is getting shared, not all possible paths, not all available paths, not the complete link status. When the link state informations are shared, it will never leave any link information. It advertises every link related information. As a result, you can see here, as a result, they can have very in-depth detail of all destinations. With that info, accurate paths can be selected. Very accurate paths can be selected. As we all know, Ospf has got a proper design pattern so that you can have a highly scalable routing protocol. Well-designed pattern. What is that? Two-level hierarchy. Two level of hierarchy. One is backbone, which will act as a transit area, and the other areas are called as non-backbone areas, or you can also call it as regular areas. So we have two-level hierarchy, transit and regular. What is the benefit of this? In this area, you may have many networks, let's say 200 networks you have. What you can do is, before sending the updates, 200 updates, you can summarize it and send on this border route. So you get a nice summarization point. Instead of advertising all 200 updates, you just summarize and send the summary. As a result, the other area need not to maintain a very big database of this area. It's not relevant for other areas. Other areas, they don't talk to this area frequently. So all that they need is only a summary route. There is no need for a detailed route. Now, because you have area, you got a summarization point. You got ABR. Because you have areas, you have ABR. A nice summarization point. As a result, the routing table entries are going to be minimized. How? Instead of sending 200 routes, you are sending only one summarized route. So the routing table of the other area routes will be minimized. Good. If your routing table is too big, then too much of CPU is going to be used in order to process every outgoing packet. Only sending the summary route. If any particular subnet goes down in this area 1, that information is localized. It is not going to be flooded to other area. That information is going to be localized. So localize the impact of topology change within an area. Next is detailed LSA flooding stops at the area boundary. As we already know, we are going to summarize. So detailed LSAs, link state advertisements, will not be sent to other area. So for this 3 beautiful reason, we need this hierarchical structure. Minimize the routing table entry, localize the impact of topology change within an area, detailed LSA flooding stops at the boundary. Next, this router A and B, how do you call it as? Backbone area router. And the number 0 is only for backbone. You cannot use any other name other than 0. No other numbers can be used. What about C, D, and E? They are in between area 0 and non-backbone. So they get a unique name called ABR, area border router. I want to say something here. There is no command specifically to say one router as the ABR. There is no command specific to say one router as an ABR. Yeah. So when an area 0 connected to a router, that automatically becomes ABR. If one connection from area 0 is made, that area becomes ABR. So it is only through ABRs we attach the other areas to area 0. Now, as I was telling you earlier, the very first thing in Ospf is finding out the neighbor. How the neighbors are discovered by exchanging the hello packet. What is the multicast address used? 224.0.0.5. So every 10 seconds, the hello packets are sent, and it is sent to this multicast address 224.0.0.5. This makes the other router to know about this router, and they learn neighbor if they are all from same neighbor, same area. I repeat, if a router to accept another router as a neighbor, what is important is the area ID should be same. There are many other things that should be same, but area ID is very important thing that we should always know. There are other things like subnet should match, authentication type, authentication string, stub. This all should match. But if someone do not know this one simple point, what? Area ID should match. That's very difficult to accept that someone as a engineer. Area ID must match to form neighbor. If you take this picture, C router is sending hello packet. With what area? Area ID 0 only because it is going from this port. Whereas in this port, it will say I'm area 1. So F also says area 1, C also says area 1, they form neighbor. Here C also sends area 0, B also sends area 0, so they form neighbor. Yes. Routers discover neighbors to exchange hello packets. Sorry, routers discover neighbors by exchanging hello packets. Yeah. Routers declare neighbor to be up after checking certain parameters. This is what I was talking about. Parameters such as area ID, subnet, authentication, timer. Timer is also very important. If I change the timer from default to something else, then I have to change it on the neighbor as well. Timer, stub, authentication type, authentication string. Actually, Ospf supports two types of authentication. Type 1 is clear text. Clear text. Type 2 is MD5. Should match. Okay. Now forming an adjacency. If you are running a point-to-point link, what does that mean if you are running a point-to-point link? When I connect to router with the Ethernet wire, this is not point-to-point. This is not point-to-point link. Then what is point-to-point link? When we connect a serial wire, which is also called as WAN link, this is what we call it as point-to-point. point-to-point link. Between these two router, which is connected via a serial link, a point-to-point link, we call it as full adjacency. Full adjacency. Next is LAN link. Ethernet links are called as LAN links instead of serial. If you have Ethernet link, you may be connecting two routers, or you may also have a switch to connect multiple routers. It's your choice. You may have two or many. Even if you have two, it is not point to point. It is multi-point. It is LAN, because the switch can be connected to a Ethernet wire. To a serial wire, you cannot connect a switch. To a Ethernet wire, you can connect a switch. Neighbor form full adjacency with DR and BDR. The router maintains two-way state with other routers. Wonderful. This is what happens when you have LAN link. Router 1, router 2, router 3, router 4, router 5. If you have like this 5 routers, these 5 are not going to form full adjacency. They are not. Only with DR and BDR, let's say this is DR and this is BDR. Only with the DR and BDR, all other routers will form full adjacency. But you see, there is no connection between 4 and 1. I did not draw. Because they are not going to have full adjacency, they will have only two-way adjacency. Two-way state is just, knowing each other with router ID. This router knows that router's router ID. That router knows this router's router ID. That's all. They don't advertise. They don't share anything. Neighbor form full adjacency with the DR and BDR. Routers maintain two-way state with other routers. We'll talk more about this in the lab. Now let us move on. Now only with the full adjacency router, the routing updates and topology informations will be given. And that DR and BDR only will distribute to all other routers. All right. So these LSAs are flooded throughout the area, but the sequence is this. Advertisement will be first given to DR and BDR, and DR will distribute it to the rest of the routers. End of the day, the LSAs are going to be flooded to all without any duplication. The reason why we have DR and BDR is to avoid duplication. More inputs, more details I will I'll explain you now in the notepad, in the paint. Let's take some routers. And let us now name it. Router 1. You see, every router will have a unique ID called router ID. We all know that if there is a loopback interface with an address, that address will be taken as the router ID. Okay, we know that. Now let us say I have a loopback interface with 1.1.1.1. So definitely that becomes the router ID of that router. Yes. So you see, every router has got a loopback interface, and they are going to use that as a router ID. And the IP address on this port is .1, .3, .5, .8, .7, .6, .4, .2. And let's say the subnet is 10.0.0.0/24. Do you understand this picture? Okay. Now tell me which router has got the biggest router ID? Exactly. 8.8.8.8 has got the biggest router ID. That becomes DR. The reason is by default it will check the priority. Priority is 1 here by default on all the routers. When the priority is same, it is going to use the router ID. It compares the router ID. Okay, so router ID is what the second preferred thing. The first priority is given to the priority. First it will check priority. Only if priority is a tie, then it will look into the router ID. In case if I set priority 10 here, this would have become DR. But now if I set priority 10, it won't become DR because DR is already elected. See, before the election starts, you should configure priority. After forming neighbor, after finishing the selection process, you cannot do that. If you do, then you have to restart all the OSPF process on all the routers. Anyway, this is DR and the next biggest will become BDR. So router 7 becomes BDR. Why do we need this in first place? Why do we need DR, BDR? If you don't have DR, BDR, then all will be sending update to all other router. And all other router will send it to their neighbors. But their neighbors have already received the update. So that becomes a duplicate and which will form confusion and loop. I repeat, when an update is received, the router will synchronize its database and forward it to other neighbor. But all other neighbor has already received. That becomes duplicate. So, what is the solution? Solution is Ospf is designed to elect one router as a leader, a designated router. And if that goes down, to support, backup designated router is also elected so that whenever some router want to send an update, it won't send to all. It will only send to DR and DR will forward it to rest of the others. In that way, duplicate is avoided. All right. Do you understand? Any question? Okay then. So we know that there is a Dijkstra's algorithm which will be running on the database and take the best route from the database for each destination and put it into the routing table. It can also be called as forwarding database. This is how the SPF algorithm works, you see. From here to go to E, this is the best path. It won't take this one, and then this one, and this one, or this one and this one. It will be too long route. Assume each link is 10 cost. If it takes this route, 10 plus 10 is 20. It will come here. If it takes the other route, 10 plus 10 plus 10 plus 10. So 10, 20, 30, and 40. Costly. So shortest path first is a binary tree algorithm, Dijkstra's algorithm, which is used to calculate the best path to reach each destination. If you assume each link cost is 10, the dotted lines, if you take, these are all costly. Maybe that can be used as backup path. Now this page explains how the OSPF router gets synchronized. You see link state updates and link state advertisements. Collection of link state advertisement is what we call as LSU, link state update. It is coming to a router. It enters into a router. Now router is going to check whether I have any entry. If it is a fresh router, just started, there won't be any entry. So what it do is, whatever came, it collects in the database. And then it will send the acknowledgement to the sender. Afterwards, it will flood this advertisement to rest of the neighbors. Afterwards, it uses the SPF algorithm to calculate the best path and put the best path into the routing table. Did you understand this? Yeah. So try to understand the other flow. Try to understand the other flow. A packet is entering. Is the entry, is there an entry? Yes means what? It is not just a fresh router, it has got some entry already. Correct. So now it will check whether the entry has got the sequence number higher or lower. If it is higher, if the sequence number is higher, then what is, I want to repeat again, listen. When an advertisement comes with sequence number, let's say sequence number is 5. You already have some entry and the sequence number is same. If it is same, ignore. If the sequence number is not same, it will check whether it is higher or lower. If it is higher, then what is incoming is higher, which means what incomes is the latest. So it will add to the database here. If it is not higher, if the incoming is not higher, what this router has got itself is latest. So it will send the information to the sender saying, you have an outdated one. Let me give mine, you copy mine. Did you understand this? Incoming sequence number, if it is higher, then what we have is outdated. We have to update. If incoming sequence number is lower, what we have is the latest. What the sender is sending is the outdated. So it has to go and send the update to the sender saying, you have an outdated one, take mine. You understand? Fine then. So apart from what we have learned, we have also something here. Every 30 minutes, update is going to be sent whether there is any change or not. Every 30 minutes. That is to make sure that everyone is in sync. All other things we have discussed, right? So is this chapter okay for you?